Okay, now let's take a look at section 1.2, number 13. So for number 13, we've got a rectangular field that's going to be enclosed with a fence. And what do we know about it? So there's, once again, we want to draw stuff so we can label our variables. We've got length and width here. There's going to be 240 meters of fencing. Okay, so what's that? That's the perimeter, which is the perimeter is the foot distance around, so it's length plus width plus length plus width. So basically 2L plus 2W, right, is the perimeter of this. So we have one equation here, that 2L plus 2W is 240 meters. Then we also are trying to find a mathematical model expressing the area of the field in terms of its length. Of course, what's area of the field? Area of a rectangle is length times width, right? But what we really want is we want a function A of L. So A of L is the area in terms of L. And if you notice, we have an L there, but this W is not in terms of L. So the question is, how can we replace that? Well, what we can do is we can utilize this equation up here. And if I divide by 2 here, I know that 240 divided by 2 is 120, and 120 equals L plus W. So if I want to get rid of my W and put W in terms of L, I can simply get everything else on the other side besides the W. So 120 minus L is going to actually equal the width. And so what I can do is take 120 minus L, plug it in here. So the area in terms of L is L times, instead of W, 120 minus L. Now, once again, we could also do this, multiply that out, as 120 L minus L squared equals the area. I'm not gonna do that. So anyway, once again, A of L, really what they're looking at, the area in terms of the length. So either A of L, or we could just call it A, is the length times 120 minus L. Well, why do I want to keep it factored? And by the way, this would be, area is going to be in square meters, right? So that would be the label on that. But the one thing that it asks is, this is a function, so we might say, hey, what's the domain of A? What could I plug in? Well, first of all, we can't have one of the sides be 0, because if one of the sides is 0, then what ends up happening is you don't have a rectangle, you just have a straight line. So L can't be 0, but it could be very close to it. It could be 1 or 1/10 or 1/100th of a meter. So not including 0, to how big could it be? Before I hit another 0, so the width could be 120 minus L. Well, if we took 120 minus 0, it'd be 120. But of course, I can get as close as I want to 0 from the positive side without actually touching it. So I can go up to, but not including 120. So that was one of the questions, I believe, is what is the domain of your function in part A? So that's part B there. So this is part A, I believe, and this is part B without really looking very close at the problem. So you can verify that I answered that correctly. Now, then it says, by plotting your graphics calculator, the graph of your function in part A. Of course, we're not going to do that, are we? Absolutely not. We're not going to do that. Why would we do such a thing? We don't have graphing calculators, so what we're going to do is we're going to use our knowledge of math here. And then it says, estimate to the nearest meter the dimensions of the largest rectangular field that can be enclosed with the 240 meters of fence. Well, what's that mean? Find the dimensions of the largest rectangular field. It's not very specific on that, is it? So sometimes you got to interpret what the book is trying to ask you. So it's not asking for the rectangle with the biggest length. It's not asking for the rectangle with the biggest width. It's asking for the biggest area. So we want our area to kind of be maximized. So we want to maximize the area of that. So what we're going to do is we're just going to look at this like a graph. And once again, I'm going to clear this, give us a little space if I can here. And so once again, we had our function A equals L times 120 minus L. And I use like a lowercase cursive L so it doesn't look like a 1. But anyway, if I wanted to multiply that out, it'd be a 120L minus L, 120L minus L squared, right? Or if I wanted to, I could write that as minus L squared plus 120L. And then if I really wanted to, I could have, you know, plus 0 on there for the constant. But if A, or A of L, is like my function, so if I rewrote this, instead of A, I called it F, or F of X is minus X squared plus 120X plus 0. What do you notice? These are the same equations here. This just happens to be a function in terms of L instead of X. But if I was to be here, you could say, hey, I could graph that thing. Of course we could graph it. Okay, so here would be the X and F of X axis, right? But instead of X and F of X, what do we really have? We have the L and A axis, or A of L axis. So L is your input, L is your input, and area is the output. And I could graph this here. So you could have, you know, of course, what is this? This is a parabola. Which way does it open? It opens downward because the leading coefficient is 0. I could also utilize the factored form of this that knows that, hey, when L is 0, I would get 0. Of course, we can't let that happen, right? So we can only go in between. So I'm going to draw an open dot there and an open dot at 120, because I can't, that's not part of my domain. I can't plug that in there, right? So the domain is, domain of A, remember, was not including 120. So for those of you that prefer this, 0 is less than or equal to L is less than or equal to 120. We can't have the equal sign there, can we? It's got to be strictly in between. So these are open dots. And then what I have is I have a parabola. Of course, the vertex of a parabola, we prove by calculus, we talk about this, occurs when x equals negative b over 2a, or in this case, L equals negative b over 2a, where b is positive 120, so it's minus 120 all over 2a. A is negative 1, so it's all over minus 2. So the minuses cancel, and that ends up being when L equals 60, which ironically is right in between 0 and 120. And what do we know? We know that's the vertex of the graph, which is either the hump or the bump, the peak or the valley. In this case, it opens downward. So what I end up having is I'm going to have a parabola that actually hits a height here at 60. So this is symmetric. Once again, these are open dots here. And I actually do hit this height here. So the question is, what is the maximum area? Well, that's when L is going to be 60. So all I got to do is plug that in then. I'm going to plug it into the top one. So in this case, and I apologize, I'm not able to change colors very easily on this yet until I figure it out. But anyway, it's going to be 60 times 120 minus 60, which is actually 60 times 60, or 60 squared, would be 3,600. Not sure what I hit there. Try and make this a little bit bigger. 60 times 60. So the area here is going to be 3,600 square meters. So that would be the biggest area. So this ordered pair is over 60 up 3,600. So the answer, 3,600 square meters, would be the biggest area. But is that actually what it asked? So we got to make sure we answer the question back in the original. It says on part C, use your graphing calculator to estimate to the nearest meter the dimensions of the largest field that can be enclosed. So the dimensions would actually be a length of 60, so that's L. So it's the answer to the question then is 60 meters times 120 minus 60. So basically L, if I can get back, L is, come on, L is going to equal 60 meters, and then the width is 120 minus L, which in this case is also 60 meters. So it's going to be a 60 meter by 60 meter rectangular field. That would be the answer to part C. And then anyway, so that should take care of this. Once again, redrawing this picture. Basically, it's an open dot at 0, 0, and over at 120, 0. And it's an upside down parabola, which very nicely peaks right here at 60, and so and up at 3600. So once again, this is the L axis, this is the A axis, or A of L axis, if you prefer that way. So anyway, hopefully that makes sense a little bit, and gives you a couple problems anyway to work on for the odds. So just label. Once again, anytime you can draw a picture, we want to draw a picture, label your variables, come up with your equations, solve those equations, and then check back in your original, make sure that your answers make sense and that we're actually answering the question. So good luck on the other odds that I gave you.